Hello everyone, this is Behnam Shariati and I'm going to guide you through this demonstration. We have prepared this demo together with my colleagues listed here from Fraunhofer HHI, with a significant part of the contribution coming from Puyan Safari. Due to the virtual format of the event, I will first give an introduction to the demonstration scenario. However, to save time for the demonstration itself, the introduction will be very short. I recommend that you read the paper and the two mentioned references on the slides to get a better understanding of the demonstration. As you may have experienced already, the unavailability of field-collected data is one of the main showstoppers in the development of reliable machine learning-based solutions in our community. Regulatory issues concerning data share is one of the key challenges. Data owners, in our case mainly telecom operators, do not tend to share their data with third parties due to conflict of interest and confidentiality concerns. However, it is of crucial importance to allow exploitation of such data while protecting the privacy of data owners. Today, we demonstrate DLFi, which addresses these challenges and enables the paradigm of shared ownership and governance of machine learning model. DLFi, the distributed learning framework, a modular, pluggable, and cloud-native solution. We define distributed learning or federated learning as the procedure of training a global machine learning model using data hosted on a set of geo-distributed edge nodes. These edge nodes are assumed to have computing resources. For the purpose of this demonstration, let's assume a multi-domain, multi-vendor ecosystem like the one illustrated here. These can be easily extended to a multi-operator ecosystem. Each domain manager has a massive amount of data collected from each domain, which are required for the development of a global machine learning model. These data, if we would like to follow the centralized learning, each domain manager has to send their data to a central location, let's say network management system of the telecom operator, where the training can take place. However, DLFi allows the network management systems to train a globally optimal machine learning model using data on every single domain manager without moving the data to a central location, therefore protecting the privacy of the data owners. DLFi reduces the amount of transported data, protects the privacy of data owners, supports different downstream tasks like QoT estimation that we showed today, vision inspection, speaker recognition, and many more, supports GPU-based acceleration, and more important, supports or enables the paradigm of shared ownership and governance of machine learning model. DLFi is mainly composed of two modules, a training coordinator node and an edge contributor node. For this demonstration, we have set up a three-node metro network comprising three ROADMs in a ring topology. We have three optical transponders, each one of them with two slots. We configured the three transponders to create three optical light paths, as you see here, interconnecting four edge computing nodes. We will take a look at the interfaces of the optical devices in a moment. Two of the edge nodes only have CPU resources, while the two NVIDIA DGX1 deep learning platforms offer GPU-based acceleration. As for this demonstration, we hosted TCN on edge node 1 and the three ECNs on the other three nodes. Therefore, two of the ECNs have access to GPU resources. We consider these three machines to represent three domain managers belonging to three vendors. Today, we will show how DLFi can train a QoT estimation model using the data hosted on three domain managers without moving them to a central location. DLFi has an eligibility check engine that determines which ECNs can contribute to the training rounds based on a few metrics, including the authenticity, the amount of the training data that is available on their host site, and the type of computing resources that are available. For the purpose of this demonstration, we consider the ECNs to be authentic and have sufficient data to contribute, but we define three scenarios for the consideration of their computing resources. In the first scenario, DLFi considers ECNs with CPU resources as eligible ones and requests them to perform the training only over CPU resources. In a second scenario, DLFi do not impose eligibility criteria to exclude the ECNs, but prioritize GPU resources if available. In a third scenario, DLFi considers ECNs with GPU resources and exclude the ones which do not have GPU availability. For the QoT estimation use case, we created a well-balanced data set using HHI's in-house network planning tool, which is equipped with the channel model to estimate the QoT metrics based on non-identical, non-Nyquist approximation of Gaussian noise model over a three-domain coordinate conus network topology. Each domain manager has relatively around 60,000 samples that is going to be used for training in our scenario. These data sets, each one of these samples include these 12 features, and we have considered 45,000, almost 45,000 validation samples, around 25% of the whole data set to be placed on the TCN for the validation purposes. We use a simple ANN with 12 input, one hidden layer of 512 neurons, and the output layer that eventually will be used for classification purpose. Now we can go to the first, take a look at the underlying metro optical network. So as you see here, we have the three metro networks, the three ROADM that are connected with three quadflex cards as the topology is discovered over the ADFA's proprietary optical line system controller. Over this metro network, we have already created three light paths, as you see, to interconnect all these four edge nodes, and all of them are in operational status, normal and operating properly. While the ROADMs are configured using this OLS domain controller, we configured the transponders on their web-based interfaces. As you see here, there are three light paths, one between quadflex 1 and quadflex 2 with the wavelengths mentioned here, and all of them are in operation normal. One light path interconnecting quadflex 1 and quadflex 3, and another one interconnecting quadflex 2 and quadflex 3. So now, as you have seen also, all the connectivity services are in place. So now what we can do, we can go and start our demonstration by running DLFi. As for this purpose, we first run the ECNs that they will then start to serve the network. Now, for the moment, let's start the ECNs one by one on each machines. So here we will use the cloud native solution of DLFi. So now we have already started the ACNs on all the three domain manager websites. So now they are serving and looking forward for the TCN to start communicating with them. Now we first start with the scenario that DLFi only uses CPU resources. So now we create it, and then we move to the visualization dashboard of the framework. The visualization dashboard has three main plots. The first one shows the CPU usage of the edge contributor nodes used by every container. This one shows the outbound traffic of the containers, and this shows the inbound traffic of the containers. So in this scenario, as you will see, all the training for the ECNs will take place over the CPU resources. That's why we see a noticeable amount of CPU utilization for every one of these ECNs. In our scenario, we use these two plots to understand when a training round starts and ends. So in this one that shows the outbound traffic at the containers, these green peaks belongs to the outbound traffic of the TCN. It's the moment that the training round starts and the TCN sends the models to all the three ECNs to contribute to the training. That's why this peak is almost 3 times the size of the peaks that are received by each containers, because it sends 3 models, one for each ECN. So, and this is peaks when the training takes place over the ECNs. The model are returned to the TCN where the model aggregation and federated averaging takes place. If you look at the CPU utilization, these yellow, orange, and blue plots showed, the blue curve showed the CPU utilization of the ECNs, and this green one belongs to the CPU utilization of the TCN, which is smaller or lower, and only belongs to the time that the TCN is actually doing the model aggregation and federated averaging. So now we go and stop this training. As you see also already here, the training has reached a very good accuracy. Now we go and we start the training configuration in which Delphi uses not only CPU, but also GPU resources. So this is the scenario number 2 that we have already identified or defined. Now, in this case, we can go back to the visualization dashboards and see the difference between this scenario and the other one. In this case, since Delphi only prioritize GPU-based resources, it will run or it will request from the ECN B and ECN C, domain manager B and domain manager C, to use their GPU resources. However, domain manager A, since it doesn't have any GPU resources, it still uses the CPU resources. That's why what you see here is that this domain manager has a high utilization of the CPU, while the utilization of the CPU on the ECN sides belonging to domain manager B and domain manager C is really negligible. And at the end of each round, we see that the TCN is performing the model aggregation and federated averaging, so there is a noticeable amount of CPU utilization. And if we look at here, we see still that there are large peaks of outbound traffic from the TCN when it sends the model to the ECNs to perform the training. And as soon as the TCNs finish the training, they send back the models to the TCN to perform the model aggregation and federated averaging. While they send the model back to the TCN, they are received by TCN sequential. So that's why here, at the end of each round, you see almost 3 peaks that shows the moment that the model are received by the TCN. Please pay attention. Here, there is a limited or very low amount of traffic exchange between different machines, while the amount of the data itself is really large compared to the small size of the models that are used or communicated between different machines. Now, in this case, let's first run the case where only training takes place over GPU. So it means that Delphi will exclude the machine that doesn't have GPU resources. So to continue with my previous discussion, here, as you see, the amount of the data that is exchanged between different machines during each training round is really negligible. In our case, we have a small data set, and we intentionally chose this small data set in order to have a few rounds of training every time, and we can cover the 3 scenarios that we had in mind within this very short time of for the virtual presentation of the demonstration. So now we see here that none of the ECNs are actually using any CPU resources during the training round. And that is because simply Delphi excludes the machines that do not have GPU, and only those ECNs who have access to GPU resources will contribute to the training. And that is also obvious here. While in the other graphs, there are outbound traffic from 3 machines, meaning that 3 machines are contributing to the training. Here we have only 2 machines, the 2 machines that have GPU resources to contribute to the training. And the same here. And here, if we compare these 3 scenarios, here, all machines are using CPU. Here, the ones who have GPU will use their GPU resources, and the ones who doesn't have GPU, which is a single one, this yellow one, uses its CPU resources. And in the last scenario, we only have the machines who have GPU resources to contribute, 2 of them, and there is no CPU utilization except the moment that TCN is actually doing the model aggregation. So this is mainly the demonstration that we would like to show. So Delphi allows the training of a machine learning model over distributed data sets with a relatively high accuracy, in all of them approaching 94% accuracy. So thank you so much. I would like to also thank the Federal Ministry of Education and Research to support our research here. These researches have also been done in the collaboration with Innovation Cluster of 5G Berlin. Thank you so much. I will be available for any Q&A after this presentation.